Good morning. Okay, now already after many long days, yes. Okay, so without wasting time, because it is a marathon, so we have to start. Okay, so I will start with optics first. So in the optics first, we have to know about the real object and virtual object. So real object, we know about that what? Real object, light ray will be always diverging. Okay, so from the real object, light ray always diverging. If they are saying any object is placed at this position, it means they are talking about the real object. And for real object, always U, what we will take? U is always negative. Okay, what is a virtual object? Virtual object we cannot. That I will discuss in the last. Okay, virtual object, they will not say like virtual object we cannot place because virtual object does not exist. So when the light ray or converging beam of light ray are going, okay, and it fall on the lens or mirror, then when they are using this statement, converging beam of light is incident on the mirror or the lens, then it means we have to take it as a virtual object. And point of convergence, like suppose that is a lens and here light ray are going, point of convergence is suppose at a distance something they have given, so that you will take the virtual object. And virtual object U, what we will take? Positive. Okay, that always it will work. Real object, object distance we will take negative, and virtual object, object distance we will take positive. Okay, what is a real image? Real image and virtual image is what? Maybe the image formed due to the reflection or refraction. If light ray are actually meeting, if light ray are after reflection or refraction, light ray are actually meeting at somewhere, then it is the real image. If they are not meeting when we are extending, so they are appear to meet at some point, so it is a virtual object. Okay, like suppose I am saying this is a convex lens, parallel beam of light is falling on the lens. After that it will converge. Now what happens here? Light ray are actually meeting at this point, so this we can say it is a position of the real image, so I will be the real. Okay, why? Because here offline class problem, what happened? Somewhere somebody is there, you have to ask to them. Okay, so I real means light ray are actually meeting. In the case of virtual object, like suppose I am taking the concave lens, now parallel beam of light fall on that. So what will happen? Concave lens is the diverging in nature, so it will diverge. When it will diverge, it will go like this. So they will not meet here. But when we extend them, so they will appear to meet in this direction. So here I can say this image is what? Virtual. Okay. So actual meeting of the light ray after maybe after reflection or refraction, that will be the real. It appear to meet or it appear to coming from the point, then it will be the virtual. So here image we will say what? Virtual. Okay. Now after that, for the mirror we have learned the mirror formula, 1 by V plus 1 by U is equal to 1 by F. And for the mirror focal length, all we take the paraxial rays, so focal length directly we can take R by 2. Okay, this is the mirror reflection formula, 1 by V plus 1 by U is equal to 1 by F. Okay, focal length for concave mirror, F concave we take negative, and F convex we take positive. Okay, lens formula, lens refraction formula. One by V minus 1 by U is equal to 1 by F. And focal length here, one, if they have, we know the object distance, image distance, so maybe we can directly use the 1 by V minus 1 by U is equal to 1 by F. Another formula of the lens focal length we have learned, what? 1 by F in air, that is equal to what? Mu minus 1 into 1 by R1 minus 1 by R2. This is the general formula for the focal length of the lens in the air, where mu is what? Mu is the refractive index of material of lens. But we don't have to remember this directly. We have to remember for the convex lens and concave lens separately. So for the convex lens, if they have given the convex lens, so here R1 and R2 are the radius of curvature. So one radius of curvature will be positive, one radius of curvature will be negative. So for the convex lens, directly we will remember what? One by F is equal to what? Mu minus 1 into 1 by mod R1 plus 1 by mod R2. So many formula you have learned, equiconvex, plano-convex, but this is the general formula that you have to remember for the convex lens. 1 by F is equal to mu minus 1, 1 by mod R1 plus 1. So whatever the radius of curvature they have given, directly we have to put their magnitude without thinking that which is the positive, which is the negative, okay? Like plano-convex, if they are saying, so 1 R1 you will take R, R2 you will take infinite. So this is the general formula that at least you have to remember this, okay? If they have given equiconvex, means both radius of curvature will be equal, so R and R you will put, then you will get the 2 by R. For equiconvex, directly maybe you mucked up the formula, F is equal to R upon 2 mu minus 1. But suppose you forget that, this you have to remember, equiconvex means R1 and R2 we will take equal, okay? And for concave, one upon F is equal to, then you will put the minus sign, mu minus 1 into 1 by mod R1 plus 1 by mod R2. For the concave, same formula is there, only minus sign we will put for concave, and for convex the focal length will be positive. That's why mu minus 1 into 1 by mod R1 plus 1 by mod R2, okay? This basic formula that we have to remember, okay? Now, if they have given the focal length in air, is equal to FA, and they are asking the focal length in any medium, that suppose it is a FM, then FM, what we'll say, FM is equal to FA mu minus 1 into mu medium upon mu minus mu medium. That is a formula we will use when they have not given the data about the radius of curvature. Directly they have given the focal length of the lens in air, and they are asking the focal length of the lens in a medium, okay? Medium, maybe you put the, in the NCERT they have given lens is put in a water. So when you put the lens in a water, so medium you will take refractive index of water. Mu is the refractive index of the material of the lens. So here they have not given the data about the R1, R2. They are asking focal length in the air, they have given focal length in the water they are asking. So FA we will put mu minus 1, mu is the refractive index of the lens, like glass, so glass they will give. Mu m is the refractive index of water, okay? After that we will get the focal length in medium, okay? Already in the class also I discussed, if suppose we are putting the lens in the same medium, like suppose the lens refractive index is the mu, and we are putting the lens in the liquid or any medium whose refractive index is the mu, then lens will be invisible and focal length will become infinite. Why? When mu and mu m are equal, then here denominator you will get 0. Denominator 0 means FM you will get what? Infinity. So lens will be invisible. That question also given in the NCERT, okay? So if the lens we are putting in a medium whose refractive index is equal to the refractive index of the lens, then lens will be invisible, or we can say focal length will be infinite, okay? Now mirror and lens combined question. So suppose I am saying if concave mirror form image whose height is 3 times of object if radius of curvature of mirror is 20 centimeter, then find object distance. Okay, so in concave mirror form the image whose height is 3 times of object. If radius of curvature of the mirror is 20 centimeter, then find object distance. Okay, so one thing here, they have given the concave mirror and it is forming the image of the height 3 centimeter, 3 times of the object. Means here magnification, directly we can say magnification is what? Magnification is the height of image upon height of object. That you will get what? 3. But we don't know, they have not mentioned here it is a real image or virtual image. Okay, sometimes what will happen, they will not mention according to the option we have to think. Okay, so here they have not mentioned image is real or virtual. Magnification, magnitude we are getting 3. So both possibilities are there. Why? Because concave mirror, it form the magnified real image also, and it form the magnified virtual image also. If they have given it form the image half of the height of the object, it means it will be always virtual. Remember that concave mirror can form magnified image of the real magnified image also and virtual magnified image also. So its virtual image will be always magnified. Dentist case I discussed in the class also. So concave mirror always form virtual image will be magnified. Virtual image will be magnified. Same will be applicable for convex lens. Okay, so magnification, magnitude we are getting 3. Now both possibilities are there. Why? Magnification is the more than 1, so either it may be the real or maybe virtual. Okay, so if I am taking, if m is equal to -3 means image is real. Okay, then m, what we will put, f upon f minus u. Okay, then m, what they have given, -3. Focal length, radius of curvature they have given 20 centimeter, but it is a what? Concave mirror, so focal length what you will get? Minus of 10 centimeter. Then focal length you will put -10 upon -10 minus u. U no need to put with a sign because already magnification and focal length we have put with a sign. So answer of the u will give the sign. Okay, 2 variable we have to put with a sign. Now then you will get what? 30 plus 3u is equal to -10. Then 3u what you got? -40. So u what you got? -40 by 3. Okay, so it means object distance we got. So if this option is there, then it is okay. Okay, means we have to go through the 40 by 3 and this image will be real. And you can see here object distance, real condition is that what? When object distance is greater than or equal to f, then concave mirror and convex lens form real image. Okay, so here object distance we are getting, we can check the answer also. Here object distance we are getting more than the focal length, because focal length they have given the 10 centimeters, so 40 by 3 is more than 10 centimeter. It means it is a real image. Okay, now other possibility is what? It may be the virtual, then it is the virtual, then m you will take 3, because For virtual image magnification is positive. For virtual image magnification is positive. This is valid for the lens as well as mirror. Okay, so then it will be the virtual. Now same formula we'll use, m is equal to f upon f minus u. Now that you will practice, you will put the values and you will get the object distance. Understood or not? So here both possibilities are there. Maybe the image is real or maybe the image is virtual. So that's why if they are mentioning like real image, then magnification you will directly take -3. If they are saying virtual image, then magnification you will take +3. If they have not mentioned, so according to the option we have to go. Everybody got? Next, if focal length of lens in air is 40 centimeter, then find its focal length in water if mu of the lens is equal to 3/2 and mu of the water I have given 4/3. One thing I said, and that you have to remember, minimum focal length of the lens you will get in air. Minimum focal length you will get in air. In any other medium, focal length will increase. Okay. So here focal length of the lens I have given in air 40 centimeter and I am asking the focal length in water. Then focal length in water, what you will say? Fa into mu minus 1 into mu water upon mu minus mu water. Okay. Now you will put the values. Fa, what they have given, Fa is equal to 40. Mu minus 1 means 3/2 minus 1. Mu W is what? 4/3 upon mu minus mu W 3/2 minus 4/3. Anybody got the answer? What is the answer? Then focal length in water you will get what? 40 into 1/2 into 4/3 upon 3/2 minus 4/3. 6 LCM, 9 minus 8. 9 minus 8, that is a 1/6. Now 6 goes, so this become 20. So 20 into 4 into 6/3. 3 2s are 6. Then what you got? 160 centimeter. So focal length in the water you got 160 centimeter. Now you can see in air we have the focal length 40. In water we got the focal length 160. So what I said, focal length of the lens will be minimum in air. In other medium, focal length will increase or power will decrease. Power will decrease. Okay. Now lens combination. So this similar question is in the NCERT. So suppose I am giving the two convex lens and one concave lens. Here focal length I have given 10 centimeter. Here focal length I have given 30 centimeter. Distance between this I have given 20 centimeter. Its focal length I am asking if the light ray is going parallel to this. Okay. And here object distance I put at 10 centimeter. Okay. Here distance I have not given. This distance suppose I am asking also. So if suppose I am saying I have the two convex lens and one concave lens. Object is placed at a distance 10 centimeter. Then we have and final ray is going parallel to the principal axis. So what is the focal length of the concave lens I am asking? Okay. So here in lens combination, when we have the lens, we will consider the refraction, one refraction from each lens. Now here when the object is at 10 centimeter, so if you see the data, focal length they have given 10 centimeter. Means this object is placed at focus. When the object is placed at focus, so how light ray go? After refraction, it become parallel. It become parallel. And when light ray is coming parallel, then after refraction, it will converge at focus. This you have to remember. When object is at focus, after refraction, then it will become parallel to principal axis. Then it will become parallel to principal axis. If parallel beam of light is fall on the lens, then it will converge at focus. Okay. Now it become parallel, so parallel beam of light fall on the second lens. Okay. So whatever the distance d is there, second lens light will fall parallel to the principal axis. Okay. Now here and here distance I have given 20 centimeter. Okay. When parallel beam of light fall on the lens, then it will converge at focus. It will converge at focus. Here object was at focus, light ray become parallel. For the second lens, parallel beam of light is falling on the lens. After refraction, it will converge at focus. So what is the focal length of this? 30 centimeters. So it will converge at focus. But distance between these two lenses are 20 centimeter. Distance between these two lenses are 20 centimeter. What is the focal length? 30 centimeter. So it has to converge at 30 centimeter. But before that, convex lens is there. Concave lens is there. Because parallel beam of light is falling on the second lens, it will converge at focus. Okay. Focal length of the second lens is 30. But distance between these two lenses are 20. So what will happen? Before convergence, it will fall on the concave lens. Now you can see here how the light ray are going. Converging beam of light is going. Converging beam of light is going means virtual object we can say. Okay. Now this will work as a virtual object for the concave lens. They are saying light ray become parallel to the principal axis. Light ray become parallel to the principal axis. Then I am asking the focal length of concave. So definition like concave lens, focus how we define? When the light ray are going parallel to the appear to converge at a point. So after refraction, it become parallel to the principal axis. Then that point is called the focus of the concave. I repeat again, concave focus how we define? When light ray are going, converging beam of light, it appear to converge at a point. Then after refraction, it become parallel to the principal axis. That is called the focus. Okay. So here total distance is the 30. This distance is the 20. So this distance what you will get? 10 centimeter. And light ray are becoming parallel to the principal axis. It means that has to be the focus. It means what is the focal length of the concave lens you got? F is equal to 10 centimeter. Concave lens focal length we say negative. That's why we will say minus 10. Should I repeat again? So here object was placed at focus. So after refraction, light ray become parallel. Parallel beam of light fall on the second lens. So it will converge at focus. Focal length of the second lens they have given 30 centimeters. So it will converge at 30. But before that we have put the one concave lens. So it will appear to converge at this point. And light ray become parallel to the principal axis. It means that point has to be the focus of the concave. Okay. Focus figure we have to keep in the mind because this type of combination they can give. Already they have given in the NCERT solved example. So this type of question may come. Okay. So focal length of concave we got minus 10 centimeter. Okay. Now lens mirror combination. Suppose I have given here object is placed at a distance of 60 centimeter from the convex lens and distance between convex mirror and the convex lens I have given 40 centimeter. If I am saying if object and image, final image coincide, then find radius of curvature of convex mirror. Okay, so object is placed at a distance 60 centimeter from the convex lens, and then distance between the convex lens and convex mirror I have given 40 centimeter. I am saying if the image and final object and final image coincide, then we have to find the radius of curvature of the convex mirror. Remember one thing, in the case of the lens and mirror combination, final image will form after the 2 refraction, 1 reflection. When only combination of the lens we have, each one reflection, 1 refraction we will take from each lens. But when we have the combination of the lens and mirror, so final image will form after the 2 refraction and 1 reflection. Okay. So here object distance they have given 60 centimeter, focal length they have given 30 centimeter. So basically this object is at what? It is a 2f. Why? Focal length 30, so this is the 2f. So where the image will form? Image will form when the object is at 2f, image form at 2f. Okay. So image will form at 60. But before 60 because distance of the mirror from the lens they have given 40. So before convergence it will fall on the convex mirror. It will fall on the convex mirror. In the case of the, like they are saying the object and final image coincide. So in the case of mirror, if they are saying final image and object coincide, so means light ray has to retrace the path. What is the meaning of retracing? How it is going or incident on the mirror and the lens, same way it has to come back. Then object and image will coincide. Again I am repeating, when they are saying object and final image coincide, it means light ray has to retrace the path. Path retracing means how it incident, the same way it has to reflect and refract back to the same point. Okay. And in the case of mirror, path retracing means incidence must be normal. When the mirror, when the light ray will incident normally, like plane mirror, simple example, when the light ray incident normally, so after reflection what happens? It will go back in the same path. So in the case of mirror, if the light ray has to retrace the path, light ray has incident normally. Okay. Then how it will incident? Same path it will go back. Okay. Now here object is at 60, so image will form at 60. So light ray will converge at 60. But before convergence, it will fall on the convex mirror. Okay. So this point will be, this distance will be 60 centimeter. Okay. Now light ray are going like this. What I am saying, final image and object is coinciding. So one refraction already I took. One refraction I took from the lens. Now what I said, final image will form after 2 refraction, 1 reflection. Okay. Now it fall on the convex mirror. Convex mirror, if object and image coincide, so it has to be normal incidence. Normal incidence means this point must be the center of curvature of the mirror. Why? In the case of the spherical mirror, normal means the line passing through the center of curvature. So here light ray has to incident normally means this light ray has to go towards the center of curvature. Then it will go back in the same path. Okay. Then this point is the center of curvature. Total distance they have given, this is we got the 60. This distance they have given 40. So what is this distance? We got this distance is the what? 20 centimeter. So radius of curvature of the convex mirror we got what? 20 centimeter. So R we got 20 centimeter. Why 20 directly we have taken? Because they are saying the final image and object coincide. Now what will happen? First refraction it is going to the 60. Now it is a normal incidence, so it will go back to the same path. Okay. Again it will fall on the lens. And then again it will come to the, because here you will take, this is the object. Now it will come to the, it is a 60, so it will form the image at 60. So final image will be formed at the same point where you have placed the object. Why? Light ray, how the light ray are going, the same path it will go back. Okay. So for the mirror, it has to be the normal incidence. Okay. Now refraction through plane surface 2-3 things we have to remember. What is the critical angle? What is the condition for TIR? These are the main thing. And when the object is in the denser and observer in the rarer, what is the apparent depth? And when the object in rarer and observer in the denser, what is the apparent height? These things only mainly we have to remember, and all the refraction, Snell's law is applicable. So Snell's law we have to remember. Okay. So anywhere like prism they are saying, any plane surface they are saying. So when the suppose object is placed at depth h and the refractive index of the medium they have given mu and observer in air, then what is the apparent depth? Apparent depth you will get is equal to what? H by mu. Directly remember that, and you have to remember in the mind. In that case, like fish and man case, you have to remember when the fish is in the water, man always observe the fish lesser than the actual depth. That's why we will take what? H by mu. When the object in air, observer in denser, and height of object is suppose h, of here denser medium, refractive index suppose I have given mu. Then what is the height of the object it will appear? So height it will object will appear at the more height, and that will be equal to what? Mu into h. So when the object in rarer air and the observer in denser, so apparent height will be mu h. You have to remember bird and fish case. When fish is the object, then the apparent depth will be lesser, h by mu. Okay. So this question, common question, it already asked in the NEET. If any object is there and it is a cube of refractive index 3/2 from one surface, it observed at a distance observed from one surface is equal to 12 centimeter and other surface is equal to 15 centimeter, then find side of cube. Okay, so here one side it appear at 12 centimeter, other side it appear at 15 centimeter. Like from here it is appear at 15 centimeter. Then what is the actual side of the cube? So this observer, suppose it observed this object at 12 centimeter. So he is observing means he will observe the apparent. Suppose actual this distance is the T1 and this distance is the T2. Okay. Now T1 by mu, what he observed? T1 by mu, he observed the 12 because object in the denser, observer in the rarer, like fish and man. So object in the denser, so what is the apparent depth? H by mu. So T1 by mu, what they have given? 12. So T1 what you got? 12 into mu. Mu is equal to what? 3/2. Then this we got the 18 centimeter. Okay. Now from this side, we'll say what? T2 by mu, that is equal to what? They have given 15 centimeters. So T2 what you got? 15 into 3/2. Then you got what? 22.5 centimeter. Now one side, this side T1 is the 18, this side is the 22.5. So what is the length of the cube? Length of the cube we can say T1 plus T2. Okay, 40.5. Now this is also a common question. It has already now 2019 they also asked in the JEE main. So here suppose light ray, white light incident, and here it is a going, green is going here. So which color will go in this this quadrant? Here we have to find the color, which color will go in this quadrant, which color will go in this quadrant. Okay, so white light incident and green, it is going from denser to rarer. Denser to rarer, white light is incident, and here green is going like this. Okay, then we have to find the color in this quadrant and color in this quadrant. So which color will get refraction, which color will get TIR. So for the TIR, we have to remember the condition for TIR. In any question, they are saying light ray will not emerge. Light ray will not emerge. It means we have to take light ray not emerge means we have to consider the TIR. Why? When the light is going from one medium to another medium. But they are saying light is not going out, not emerging. It means that light ray is getting the TIR. Okay. For the TIR, we have to remember angle of incidence must be greater than critical angle. Angle of incidence must be greater than critical angle. Then light ray will not go out in the other medium, it will get TIR. Okay. Now this angle of incidence, green is going at just grazing the surface. It means angle of refraction for the green is 90. It means this angle of incidence is the critical angle for the green color. Okay. So basically I can say what? Angle of incidence must be greater than theta C. And incidence angle is what? Theta green. It is a critical angle. I am saying, suppose theta G I am taking critical angle for green. Okay. So theta G, here angle of incidence is equal to theta G. That is the critical angle of green. How we decide? Because green they are saying it is going like this. So what is the angle of refraction for the green? 90 degree. So it means incidence angle is the critical angle for the green. Now for the TIR, what is the condition? Now green, we know that green is going through the what? Tangential to the surface. Now other color we have to check. Which color will get TIR? Which color will get refraction? So if you see, like green is going this. So this angle of incidence is the critical angle for green. For other color, now I am applying the condition. I has to be greater than critical angle for other color. For other color, I am saying. For which color? Critical angle of incidence will be greater than critical. It will get TIR. Okay. Now what is the angle of incidence here? Angle of incidence here is the theta green. Theta green is greater than critical angle. Okay. When you get the critical angle on any side, always next step is what? We have to apply the sine. Now sine theta G must be greater than sine theta C. Okay. Now sine theta G means it is a sine of critical angle of green. Critical angle and mu relation we have. Sine theta C is equal to 1 by mu. Sine theta C is the 1 by mu when rarer medium is air. Rarer medium is air. Okay. Now sine theta G we can say what? 1 by mu G is greater than 1 upon mu C. Now from this we got what? Mu C has to be greater than mu G. Means which color refractive index will be greater than the refractive index of the green color? That color will get TIR. That color will get TIR. So whose refractive index, which color refractive index we can say, or for which lambda mu will be greater than green. So mu and lambda relation is what? Lambda more, mu will be less. Okay. So here mu I need more. Mu I need more means lambda has to be less. So which lambda is less than lambda of the green? They will get TIR. So means which lambda? Violet, indigo, blue. Violet, indigo, blue. Their lambda is less than lambda green. Lambda green lesser, so mu will be more. So VIB will get TIR. Okay. And YOR will get in this, YOR will get refraction. So that's why here we will get the YOR and here we will get the VIB. Okay. This question they can ask in the prism also. This they can ask in the plane surface. Already what I said, in the prism they ask in the 2019 or 21, they ask in the JEE main. So that type of question they can repeat. Okay. Now optical instrument, telescope and microscope. So simple microscope I'm not saying. So first I'm writing the formula for all. Compound microscope, magnifying power. Okay, so different cases are there, different cases. Mainly we have to remember the two cases. One is what? First basic formula is what? M is equal to MO into ME. What is the MO? Magnification for objective. And ME is what? For eyepiece lens. Okay, MO, like it is a lens, so directly we can use the relation. In compound microscope, objective always form the real and magnified image. Objective always form real and magnified image. So MO will be, it will be the real image, and eyepiece will always form the virtual. So for the real image, magnification is negative. For virtual image, magnification is positive. So overall magnification will always come negative. If negative and positive option is there, we will go through the negative option. Why? MO real, ME virtual. Means objective will form the real image, eyepiece will form the virtual image. Real image magnification will be negative. For virtual image, it will be positive. So negative into positive, overall then you will get the negative. Okay. So this we can say what? VO by UO, its magnitude directly I am writing into ME. ME, different cases are there. Basic formula is what? D by UE. D by UE. UE is what? Object distance from eyepiece. And we will put the minus sign. Why? Overall magnification we will get negative. Okay. Then M, what we will get? M is equal to, at particular cases, when final image is formed at infinity, then UE what we will take? UE we will take FE. Then M what we will get? M is equal to minus VO by UO into D by FE. All only magnitude you will put. So when final image is formed at infinity, then ME what we will take? D by FE. Why? When the object is at focus, then image will form at the infinity. Then magnification formula we will use minus VO by UO into D by FE. Means for the objective directly we have to use the lens concept. Magnification is the what? V by U. For eyepiece we have to remember the condition what? D by UE. When final image is at infinity, only eyepiece magnification will change. When final image is at infinity, D by FE. When final image is at capital D, then M is equal to what? Minus VO by UO into 1 plus D by FE. And this we can say it is a maximum magnification for eyepiece. 1 plus D by FE is the maximum magnification for eyepiece, or we can say it is a maximum magnification for the simple microscope. 1 plus D by FE is the maximum magnification for the simple microscope, or we can say it is a maximum magnification for the eyepiece. Okay. For microscope, objective and eyepiece, we take both as a both of a small aperture and small focal length. Why? Microscope we use to focus on the near object. That's why we don't require the more aperture, because more aperture you will take, so other defect will come like chromatic aberration and all. That's why for microscope we select the lens, objective and eyepiece. Those has the small aperture and small focal length. Okay. Then separation between lens. that we will say what? Separation between the lens VO plus UE. This is the general formula, VO plus UE. Now when final image is at infinity, then separation we will say VO plus FE. Okay, why final image is at infinity, so UE has to be FE. Okay, and second is what? When final image is at capital D, then separation we will say mod of VO plus FE into D upon FE plus D. Okay, this formula relation directly you have to remember. Separation between the lens, if they are we needed, so separation we can say general formula is what? VO plus UE. If they are saying final image is at infinity, so UE we will take FE. If they are saying final image is formed at capital D, then UE what will take? FE into D upon FE plus D. VO will remain as it is. Okay, that is a separation between the lenses. Now if suppose I have given if focal length of objective and eyepiece in compound microscope is 1.2 centimeter and 2.5 centimeter. If object is placed at 1.5 centimeter from objective, then find okay 1.5 centimeter from my objective, then find magnifying power. Okay, if in the case of microscope they have not mentioned where the final image is formed, then we will take always final image is formed at capital D. In the microscope, if they have not mentioned where the final image formed, we will always take the final image is formed at capital D. Okay, so here we will consider the final image is formed at capital D. Now focal length of the objective they have given, eyepiece they have given, and object distance from the objective they have given. So first what we will do, we will find the MO. Okay, so MO how we will get? So for the MO we require UO they have given. UO is equal to minus 1.5 centimeter. Minus 1.5 centimeter. This is a UO. Okay, and VO I required. Focal length of the objective they have given 1.2 centimeter. Remember one thing, objective has to form the real image. Objective has to form the real image of the object. That's why for the objective, object distance will be always greater than or equal to F. Already I said this. For the concave mirror and convex lens, if they have to form the real image of the real object, then object distance must be greater than or equal to focal length. So here you can see object distance I have given 1.5, focal length I have given 1.2. It means object distance is greater than focal length. Then only objective will form the real image of the real object. Okay, so it is required, it is a necessary that object distance from the objective must be greater than the focal length of objective. Then only it will form the real image, and that real image will work as the object for the eyepiece. Okay, now we have the focal length, we have the object distance, then we can find the image distance 1 by VO minus 1 by UO. Minus minus become plus 1 upon 1.5. Directly I am writing that is equal to 1 by F. 1 by F is what? 1.2. Now 1 by VO what you will get? 10 by 12 minus 10 by 15. Okay, then we can take what? 60 LCM. So 50 minus 40. Okay, then what we got? VO is equal to 60 by 10. Then we got the VO is equal to 6 centimeter. Okay, so VO we got the 6 centimeter. From that, MO you can get MO is equal to minus of VO by UO magnitude. So VO what we got 6 and UO what we have 1.5. So this you got minus 4. Now magnification for the objective, if they are asking directly, we got the 4. But magnifying power of the microscope they are asking. So final image, what I said, if they have not mentioned, we will consider at capital D. So when the final image is at capital D, then ME what we will take? ME is equal to 1 plus D by FE when final image is as capital D. So that is equal to what? 1 plus D is what? 25 centimeter, and FE what they have given? 2.5. So 2.5, that is a 10. So what we got? 11. So ME we got 11. MO you got 4. So what is the overall magnifying power? Magnifying power M what you will get? MO into ME, that is equal to minus 44. Okay. So this is the magnifying power of the compound microscope. Completed? Okay. Now telescope formula, what magnifying power telescope we have to learn. Normal adjustment, that is equal to what? FO by FE. So for the telescope, okay, number one, that magnifying power when final image is formed at infinity, then M we write as what? Minus FO by FE. And second, if final image, and here separation also we have to remember, separation between the lens we take. FO plus FE. Simple question they can ask on this relation for the telescope. If they are asking the easy question, so they will definitely ask from this formula, minus FO by FE and FO plus FE. Okay, so they will say the length of that or the length of the tube or length of the telescope is this, and magnifying power is this. Then what is the focal length of the objective and eyepiece? So they have not mentioned anything. So final image you will take in this case telescope. If they have not mentioned, final image we will take at infinity. So for the normal adjustment or final image is at infinity, magnifying power we can say minus FO by FE, and the separation between the lenses we can say FO plus FE. Simple question they can ask on this formula, so remember it, FO by FE and FO plus FE. So if final image is at capital D, then magnifying power will say minus FO by FE into 1 plus FE by D. That is a magnifying power when the final image is formed at capital D. And separation we will say FO plus FE into D upon FE plus D. Okay, that is a separation. This already we have learned. UE we will replace by FE into D upon FE plus D when they are saying final image is formed at capital D, whether it is a compound microscope or telescope. When final image is formed at capital D, UE we can replace by FE into D upon FE plus D. Okay. But if they have mentioned the object distance from objective, they have not said the object is at infinity. Like they have given the object distance, it is a comparable to the distance of focal length of the objective. So all these formula will not be valid. Then we have to do what? we have to go through the, like suppose one question directly I am saying, if objective and eyepiece focal length is 40 centimeter and 5 centimeter in telescope. If object is placed at 2 meter from objective, then find length of telescope. Okay, if final image is formed at infinity. Okay, so here if objective and eyepiece focal length they have given 40 centimeter and 5 centimeter, and the object is placed at 2 meter. If 2 meter means 200 centimeter, 200 centimeter is not very large in comparison to 40 centimeter, then in that case we cannot apply any formula what I have learned. In this case what we will do, object distance from the objective you will take minus 200 centimeter. Okay, focal length of the objective they have given 40 centimeter, and by using this you will find the VO. You will find the VO. 1 by V minus 1 by U is equal to 1 by F. So you will get the VO. After getting the VO, they are saying the final image is formed at infinity, so you have to find the length of the telescope. Length of the telescope, what we will say? L is equal to mod of VO plus UE. UE you will write, but they are saying final image is at infinity, so then you will write here FE. Okay, so in this case we will not use the FO plus FE because final image is formed at infinity, so length of the telescope we will say FO plus FE. That we will take when the object is at infinity, or object distance they have given very far, like 3 kilometer, 5 kilometer, 10 kilometer from the objective, means that distance is very large in comparison to objective. So in that case directly we can use the formula like length of the telescope FO plus FE, or magnifying power we can say FO by FE. Okay, when final image is formed at infinity. But if they have given the distance of the object is comparable to the focal length, we will not use those formula. First we will find what? We will apply the length formula for the objective. 1 by V minus 1 by U is equal to 1 by F. We will get the VO, and according to the final image, suppose they are saying final image is formed at capital D, then here we will write FED upon FE plus D. Here if they are saying final image is at infinity, then here we will write the FE. Okay. Now wave optics, that YDSE is important, and this year chance is there YDSE, or maybe they will ask the polarization any question. So YDSE, 2-3 things we have to remember, and more chances what they will ask the like two different wavelengths at any point they are coinciding, what is the like distance or what is the ratio of the number of bright fringes. So 2-3 things I will say in the YDSE. So first thing what, suppose we have the two sources S1 and S2, distance between the sources, we take the small d, this is the screen, and this O point is the bisector. Okay, now any point P I am taking on the screen. So this point, the wave are traveling to a different distance. Okay, if point P distance from the bisector I am taking Y, then we have to remember the path difference at P. Path difference at P, that we can say delta X is equal to two relation I am writing in the terms of theta. If P point I am joining with the bisector of the slit, and this is making an angle theta, this distance we write as the capital D, and the condition we have capital D must be greater than greater than small d, means distance between the screen and the slit must be very large in comparison to the distance between the slit. This angular position of the point, if they are asking, so angular position of the point P is what? Theta, I have mentioned. So in the terms of angular position, we can write the path difference is d sine theta. So if they are asking the angular position of the point P, then, or angular position of any minima, maxima, or any point they are asking, then angular position means they are asking the theta. So theta, for the theta, what is the path difference? We will write d sine theta. If they are asking distance of the point P, distance of the point P, distance, all the distance we will measure from bisector. If they are asking the distance, it means they are asking the y. Then delta x, what we will write? Dy by capital T. These two formula you have to remember in the terms of theta, angular position of the point P, angular position of P, that is equal to what I have taken? Theta. So in the terms of angular position of the point P, what is the path difference? Delta x is the d sine theta. In the terms of distance on the screen, like y I have taken the distance of the point from bisector. In the terms of distance, we can write dy by capital D, dy by capital D. Okay. Second thing in this we have to remember, what is the central maxima? Central maxima is the point where path difference is equal to 0. Central maxima may or may not be the bisector. What is the definition of the central maxima? Central maxima is the point where the path difference is 0. Central maxima is the point where the path difference is 0. It may or may not be the bisector. It may or may not be the bisector. That depends on, if the no path difference is there at the bisector, bisector will be the central maxima. Okay. Number 3, if two wavelength lambda 1 and lambda 2 are using in YDSE, then their maxima will coincide if n1 lambda 1 is equal to n2 lambda 2. This relation is important, and it is possible that question will come from this relation, n1 lambda 1 is equal to n2 lambda 2. Two wavelength they will say, and they will ask which maxima of the this wavelength, which maxima of the this wavelength will coincide, or what is the distance of this maxima from the bisector. Okay, means two wavelength they are using and they are saying they coincide. So they coincide means we can use the relation n1 lambda 1 is equal to n2 lambda 2. Okay, because for maxima delta x must be equal to n lambda, where n is the number of maxima. Don't get confused from the diffraction. For the interference YDSE, for the maxima, what is the path difference? N lambda. First maxima lambda, second maxima 2 lambda, third maxima 3 lambda. For central maxima, n will be 0. Okay, and for minima, delta x is equal to 2n minus 1 lambda by 2, where n is the number of minima. Okay, these are the main thing that we have to remember in YDSE. And one last relation, if slab of thickness T is placed in front of one of the slit, then central maxima will shift towards that slit. Okay, so if slab of thickness T is placed in front of one of the slit, then central maxima will shift towards that slit and path difference in that case we will say T into mu minus 1. Okay, delta x due to the slab will be due to slab. Delta x path difference we will get t into mu minus 1. Okay, and if they are saying how much maxima got shifted, so this delta x we will equate with t into mu minus 1, we will equate with n lambda or dy by capital D. Remember that if they are asking how many maxima got shifted, then we will equate with n lambda, and is the number of maxima got shifted. Okay, and if they are asking the distance, how much central maxima got shifted, how much distance central maxima got shifted, so dy by capital D. Okay, why they are asking, then distance they are asking, so dy by capital D you will equate with t into mu minus 1. If they are asking the number of maxima shifted, then you will equate with n lambda. Now one question we'll do in that. If glass slab mu is equal to 3 by 2 of thickness T is equal to 2 lambda by 3 is placed in front of one of the slit, then find ratio of intensity before and after placing slab. Ratio of intensity at bisector, suppose I am saying. So if glass slab of mu is equal to 3 by 2 of thickness T is equal to 2 lambda by 3 is placed in front of one of the slit, then we have to find the ratio of intensity at bisector before and after placing the slab. So before placing the slab, you are putting in the front of the upper slit or lower slit, doesn't matter. In front of any of the slit, you are putting the slab of thickness 2 lambda by 3. Now they are asking, what is the ratio of the intensity at the bisector? They are asking the ratio of intensity before putting the slab and after putting the slab. Okay, so before putting the slab at bisector, we will get the central maxima. Before putting the slab at the bisector, we will get central maxima. At central maxima, intensity will be maximum. That will be, suppose I am taking I naught. Okay, so before putting slab, intensity at bisector we will get what? I naught. That is a maximum intensity. Why? Because central maxima path difference is 0, path difference will be 0, so phase difference will be 0, so we will get the intensity maximum. So before putting the slab, intensity at the bisector was the central maxima before putting the slab. So at central maxima we have the intensity, suppose I naught. Now when we put the slab, so what the slab will do? Slab will produce the path difference. How much path difference it will produce? It will produce the path difference T into mu minus 1. It will produce the path difference T into mu minus 1. So delta x, what we will do? Delta x is equal to T into mu minus 1. Now delta x, T they have given what? 2 lambda by 3. Mu is what? 3 by 2 minus 1. Then what we got? 3 by 2 minus 1 by 2, that is equal to what? 1. So 3 by 2 minus 1 by 2, so you got the, 1. 3 by 2 minus 1, then you got the 2 lambda by 3 into 1 by 2. So 2 and 2 cancel out, we got the lambda by 3. Okay. So at the same point, what is the path difference now? The path difference now due to the slab, at that point, what is the path difference? Lambda by 3 at bisector. Why? Because at bisector, due to the geometry, no any path difference is coming. Bisector means from the S1 distance is equal and S2 they are traveling the equal distance. So before putting the slab, it was the central maxima because path difference was 0. But when we put the slab at the same point, some extra path difference came. How much extra path difference came? T into mu minus 1. That we got lambda by 3. Now at the same point, we will find the first phase difference. So delta phi we have relation 2 pi by lambda into delta x. So delta phi what we will say? 2 pi by lambda, and delta x at that point we got the lambda by 3. Then we got the delta phi is what? 2 pi by 3. Okay, means at the same point at the bisector we got the phase difference is what? 2 pi by 3. Now for the resultant we will use the formula IR is equal to what? Or I2 I can use. I2 is equal to I naught into cos square delta phi by 2. This is the formula of the resultant intensity in the interference when the both sources have the equal intensity. I is the I naught maximum intensity into cos square delta phi by 2. Delta phi by 2 what you will get? 2 pi by 3 by 2. So 2 and 2 get cancel out. So you got the I naught into cos square pi by 3. Cos pi by 3, cos 60 degrees the 1 by 2. 1 by 2 square you will get the 1 by 4. So you got I naught by 4. Now what is the ratio of the intensity? Initial I naught. Now at the same point how much intensity we have? I naught by 4. So what is the ratio? 4 is to 1. So ratio will be I1 by I2 is equal to I naught upon I naught by 4. That is equal to what? 4 is to 1. Okay. Time is going very fast. Now polarization, only one thing, two law we have to remember. One is the Malus law and one is the Brewster law. Malus law for the polarization he has given. So for the Malus law, suppose we are using the polarizer. Okay. Polarizer is what? It is a device that is used to convert the unpolarized light to the polarized light. Okay. So we have to remember this is a solid example. If unpolarized light of intensity I naught, unpolarized light of intensity I naught incident on the polarizer. So first polarizer will always transmit half of the intensity. So first polarizer will always transmit how much? I naught by 2 without thinking about the direction of the axis or anything. If unpolarized light fall on the polarizer, so only half intensity will get transmitted. So how much absorb they are saying? So half is the absorb. How much is the what? Because I naught by 2 transmitted, so I naught by 2 has cut. Okay. So I naught by 2 first polarizer. If unpolarized light incident on the first polarizer, without thinking anything, we have to transmit I naught by 2. After that, we have to apply the Malus law. What is the Malus law? Like suppose axis of the first and second polarizer making an angle theta. Okay. So whatever incident after the when unpolarized incident, then it become I naught by 2 and it become the plane polarized light. So when the unpolarized light fall on the polarizer, so transmitted will be the plane polarized light of intensity I naught by 2. Now when you have the PPL, then if you are putting the polarizer, then what will happen? Whatever the then we will apply the Malus law. PPL means plane polarized light incident on the polarizer and the axis is making the angle theta. Then how much transmit? Incident, whatever incident into cos square theta. So what incident here? I naught by 2 into cos square theta. Okay. First polarizer, it passes the I naught by 2 because unpolarized light incident. After that it is a plane polarized light. So first, then we will apply the Malus law. Malus law is what? Incident into cos square theta. What is the theta? Angle between the axis of the both polarizer. Now again it come, how much intensity came out? I naught by 2 cos square theta. Suppose I put the third polarizer and first polarizer, their axis is at 90 degree. This situation is called the polarizer crossed each other. Polarizer crossed each other means transmission axis angle will be what? 90 degree. Okay, so angle between the first and last is the what? Transmission axis is the 90. So what is the angle between the second and third? Second and third angle will be what? This is the theta, so this angle you can say what? 90 minus theta. Then angle between the second polarizer and third polarizer will be 90 minus theta. So what I said, after that whatever incident into cos square theta. So what is the incident here? I naught by 2 cos square theta. So I naught by 2 cos square theta incident. Okay, what is the angle between the second and third polarizer? 90 minus theta. Then cos square theta, you'll say cos square 90 minus theta. I repeat again, second polarizer, how much it is transmitting? Second polarizer is transmitting I naught by 2 cos square theta. What I said, when you are applying for the PPL, whatever incident into cos square theta. So incident here is what? I naught by 2 cos square theta on the third polarizer. So incident into cos square theta. What is the theta there? Angle between the axis of the polarizer. Here angle between the axis of the polarizer is what? 90 minus theta. So that's why I put here 90 minus theta. Then what we got? I naught by 2 cos square theta into cos square 90 minus theta means sin square theta. Okay, remember this result directly when they have given the first and third is crossed each other and the angle between the first and second is theta. Directly remember intensity is the what? I naught by 2 cos square theta sin square theta. Further we can solve more that result directly. Remember, if I multiply this by 4 and divide by 4, so we will get what? I naught by 4 I divided, it become 8 into 4 sin square theta cos square theta. 2 sin theta cos theta. 2 sin theta cos theta, what I can say? Sin 2 theta. It is what? 4 sin square theta cos square theta. It means I can write this sin square 2 theta. So that is become I naught by 8 sin square 2 theta. Remember that it is a transmitted intensity. Because this is the solved example, so maybe same result they can use. I transmitted is equal to what? I naught by 8 sin square 2 theta. This result when we can use? When first and third polarizer crossed each other and the angle between the first and second is the theta. Then what is the transmitted intensity? We can say I naught by 2 sin square 2 theta. Okay. And at what theta, what is the angle between the first and second polarizer so that transmitted intensity will be maximum? So if they are asking this is the maximum, so sin 2 theta has to be maximum. So sin 2 theta will be 1. So 2 theta is the 90. So theta is equal to 45. So when the angle between the first and second and third is the 45 degree, then transmitted intensity will be maximum. How much maximum transmitted intensity? So sin 2 theta is 1. So transmitted intensity will be I naught by 8. Okay. So if this situation they have given like first and third are crossed each other, angle between the first and second is theta. So directly IT value you can use I naught by 2. What is the I naught? Intensity of the unpolarized light. Okay, whatever the numerical value they are giving, numerical value we will put here. I naught by 8 sin square 2 theta. From that we can get the angle between the first and second polarizer as well as second and third polarizer. A polarizer making angle with what? A polarizer making angle with what? Which polarizer? First polarizer, whatever the orientation. First polarizer, whatever the orientation, it doesn't matter. Always first polarizer, whatever the orientation, it will always transmit I naught by 2. First polarizer, whatever the orientation is there, it will transmit I naught by 2. After that, theta, what I am taking, angle between the axis of the first and second. Then we will start applying the Malus law. First polarizer, no need to mention what is the orientation. Whatever the orientation of the first polarizer, always transmitted intensity from the first one is the I naught by 2. If unpolarized light incident on the first polarizer. If unpolarized light incident on the first polarizer, always transmitted will be the I naught by 2. Okay, doesn't matter what is the orientation. Okay, second thing, when we are talking about the polarization, so actually light, we are talking about the light has the electric and magnetic field vector. So polarization means electric field vector because our eye is sensitive for the electric field. Okay, so when they are talking about the polarization, means electric field vector get polarized. Electric field vector get polarized. Polarization, everybody know what is a plane polarized light. So when they are saying which vector, which component of the EM wave, electromagnetic wave or light wave get polarized. So polarization, when we are talking about, it means electric field component of the EM wave or light get polarized. Understood or not? And second, we have learned the Brewster law. Brewster law means if it is a rarer and denser refractive index mu, if light ray incident at a particular angle theta p, or that I say IP, okay, some light ray will get reflection, same angle, law of reflection, and light ray got refract, that is a suppose R. So when angle of incidence on the interface of rarer and denser medium is equal to the polarizing angle, that IP P for the polarizing angle. When angle of incidence on the interface of the rarer and denser is the polarizing angle, then 2-3 things we have to remember. Reflected ray will be completely polarized. Reflected ray will be completely polarized. So polarization angle definition is what? One definition we can say what? The angle of incidence on the interface of rarer and denser medium, so that reflected light is completely polarized, reflected ray is completely polarized. So that angle of incidence is called polarizing angle. Okay, this I have mentioned the reflected ray. And dot means what? All the vibration lie in a perpendicular to the plane. All vibration lie perpendicular to the plane. Okay, so here reflected ray is completely polarized. Reflected ray is completely polarized. So then angle of incidence is called the polarizing angle. Okay. When angle of incidence is polarizing angle, then reflected ray and refracted ray will be 90 degree. Will be, what is the angle between them? 90 degree. So when angle of incidence is polarizing angle, so reflected ray and refracted ray will be perpendicular to each other. So two things we have to remember. When the angle of incidence is equal to polarizing angle, then reflected ray will be completely polarized, one thing. Second thing, reflected ray and refracted ray will be perpendicular to each other. Like suppose they have given the mu relation, okay, and they are asking what is the angle of refraction, or what is the angle between the R and this. So if they have given the angle of incidence is the polarizing angle, so directly we can say reflected ray and the refracted ray will be perpendicular to each other. Okay, and by using this relation mu, we got what? Mu is equal to tan IP. What is the mu? Refractive index of the denser medium with respect to the rarer medium. What is the mu? Refractive index of the denser medium with respect to the rarer medium. Means mu, we can say mu d by mu r. Most of the cases mu r they take the 1, so directly we can take the mu is equal to tan IP. Mu is equal to tan IP if rarer medium is air. Then mu you will get tan IP. This relation you have to remember. And polarizing angle, two condition: reflected ray will be completely polarized, and second thing is what? Reflected ray and refracted ray will be perpendicular to each other. Okay, and mu is equal to tan IP. We know that denser medium refractive index is always greater than 1, so means tan IP will be always greater than 1. So polarizing angle will be always greater than 45. This is the order of range of the polarizing angle. Polarizing angle will be always greater than 45 and less than 90, because tan 90 is infinity. So it will be always like more than 45. Why? Tan 45 is 1, but it is a denser medium, so denser medium refractive index will be more than 1. So that's why mu will be always greater than 1. So it will be always greater than 45 up to the 90. This is the range of the polarizing angle. Okay. After that, Snell's law, everybody know. Snell's law you can apply if they are asking the question, and according to that we can find the, they are asking the polarizing angle, they are asking the angle of refraction, they are asking the angle of reflection, all we can find. But we have to remember directly means at the angle of incidence, when the polarizing angle, then reflected ray will be completely polarized. Okay. Now come to the semiconductor. One last one more thing, like resolving power and resolving limit. Resolving power and resolving limit of the telescope is important. So resolving power and resolving limit is what? Resolving limit is the minimum distance between the two objects that any optical device, any optical instrument can separate. Okay, that is called the resolving limit, and ability to separate them, that is called the resolving power. For the telescope we use the telescope angular resolving limit. Angular resolving limit delta theta is equal to 1.22 lambda by d, where d is the diameter of telescope. Its unit you will get in radian. If they are asking the angular or option they have given in radian, then angular resolving limit will use delta 1.22 lambda by d, where d is the diameter of objective lens. Okay. If the option they have given in meter, centimeter, micrometer, then they will give the distance between object and objective. Okay. So if distance between object and objective is equal to capital D, then resolving limit we can say what? 1.22 lambda by small d into capital D. Like they have given the distance of the moon from the earth is this, and lambda and all, and diameter of the objective lens they have given. They are asking the resolving limit, so 1.22 lambda by d is the diameter of the objective, and capital D we will put the distance between the objective and the moon. Okay, so if they have given the option in micrometer, meter, centimeter, it means they are asking what? Linear resolving limit. That we will use this formula. If option they have given in the radian, it means they are asking the angular resolving limit, so we will use only what? 1.22 lambda by d, where d is the diameter of the objective. Okay, then resolving power, directly we will say what? Resolving power, if you know the linear resolving limit, so resolving power directly we can say the reciprocal of that. So resolving power of telescope we can say one upon resolving limit. When angular resolving limit, so we can use the proportionality. Okay, when we don't know the distance between them, we can use the proportionality. Otherwise, directly we can say the resolving power is the reciprocal of resolving limit, and this is the linear resolving limit. Okay, then you will get what? Small d will go up into 1.22 lambda into capital D. This we can use the resolving power of the telescope. Okay, so telescope you can see resolving power is inversely proportional to the lambda for the given distance, like moon and earth distance is fixed, diameter of the objective is a constant, so resolving power is inversely proportional to lambda. Okay, now lambda, if they are using, so lambda how we can change in the, like in a compound microscope, electron microscope, again the same thing you will get. Resolving power is inversely proportional to lambda. In electron microscope, lambda you will relate with de Broglie wavelength. Lambda you will relate with de Broglie wavelength. So like I can say directly, resolving power is inversely proportional to lambda. Okay, in electron microscope, lambda you will say what? De Broglie wavelength, h upon m into v, and that I can say h upon under root 2mk. K I can say what? H upon under root 2m e into v. Maybe they will give the potential difference. Maybe they will give potential difference. So we can say lambda is inversely proportional to under root v, where v is the potential difference. Okay, so lambda inversely proportional to v. So what we can say here from that, resolving power is inversely proportional to lambda, and lambda is inversely proportional to v, root v. So resolving power will be directly proportional to under root v. Okay, now suppose they are saying initially the voltage was the 2 kilovolt, now it becomes the 32 kilovolt. If the initial resolving power is R, then what is the new resolving power? Then we can directly use the R1 by R2. R1 by R2 is equal to under root of V1 by V2. This relation is important. Resolving power is inversely proportional to lambda. Okay. Otherwise, they can use the two different wavelengths and directly they can ask what is the ratio of the resolving power. Or if they are giving the potential difference, we will relate with the de Broglie. In the case of electron microscope, they will ask. So for the electron microscope, lambda inversely proportional to root V, where V is the potential difference. And then resolving power ratio, what you will get? Under root of V1 by V2. Okay. Semiconductor, mainly theoretical question they are asking from the PN junction and this. So I will discuss the theory mainly. So semiconductor, intrinsic, extrinsic. We have the idea intrinsic means pure semiconductor. Mainly we have to discuss the two semiconductors, silicon and the germanium. Okay. So pure semiconductor is called intrinsic semiconductor. And when we add the calculated amount of impurity, in the intrinsic semiconductor, so that process is called the doping, because randomly we cannot put the impurity. Impurity means what? We are adding the trivalent or pentavalent atom. When we add the trivalent or pentavalent atom in the intrinsic semiconductor, so then what happens? Their conductivity increases very high. We are mixing the small amount, but the conductivity increases more. So that type of semiconductor is called the extrinsic semiconductor. Intrinsic, pure, means pure silicon, pure germanium, we can say intrinsic. When we add any trivalent or pentavalent impurity in the intrinsic semiconductor, that is called the extrinsic semiconductor. Okay. Semiconductor, majority, like here, what in the semiconductor, what happens? So we have the idea about the energy band. Energy band is what? We define the energy because some atom has the two electron in the outermost shell. Okay. So in the, suppose any sample of the any silicon, suppose I have, so it has the large number of atom electron will interact each other. So what will happen? If suppose I have the n atom, so n atom outer shell, outer shell, suppose 4 electrons are there, outer shell 4 electrons are there, and I have n atom. So all the 4 electron of the outer shell, they will interact with the other atom. So energy of all the electron will be different. So what will happen? We will not get the sharp energy. Because all 4 electron and all 4 electron of all the atom, it will not be equal. So due to their interaction, what will happen? Energy will be different for the different electron. That's why we say the energy band. Because valence band means what? It contains all valence electron, one thing. And all the valence electron in n atom, suppose you have the sample of n atom, all the n atom 4 electron does not have the same energy. That's why how many energy level we can get? Each atom 4 electron, okay, and total how much I have? Total n atom I have, so how much total energy state in the valence electron we will have? 4n. That's why different energy levels are there, so that's why we call it the energy band. So energy band means it is not a sharp defined energy. What? Different electron may have the different energy. So maximum possible energy what we can have? 4n. Because if I have the sample of the n atom, so each atom has the 4 valence electron, 4 different energy state may have. So n atom will have 4n energy state. Okay. So that's why it is called the valence band. Now valence band contains the valence electron. They have made the covalent bond with the nearby atom. Now another energy level we define the conduction band. Conduction band is what? Those contain the conduction electron. Those contain the free electron or the conduction electron. Okay. At absolute zero, semiconductor conductivity is what? Semiconductor conductivity is 0. At absolute 0 or 0 Kelvin, we consider the semiconductor conductivity 0. But at room temperature, what will happen? Some electron will get free. So what will happen? They will go to the conduction band. So at room temperature, they will have some conductivity. Okay. Energy difference between the valence band and the conduction band is called the forbidden gap. Forbidden gap, maybe in the case of metal, conduction band and valence band may coincide also. Maybe they will have some gap, but that gap will be very small. In the case of semiconductor, it is more than the conductor but less than the insulator. For insulator, energy band gap will be more than 3 electron volts. So for the insulator, if you want to conduct the electricity, we have to apply the more very high electric field, then the electron will jump from the valence band to the conduction band. Okay, that is the band theory of the semiconductor. Now intrinsic means pure semiconductor. Pure semiconductor conductivity is small, but when we add the trivalent or pentavalent atom as a impurity, so their conductivity increases large amount. So those semiconductor is called the extrinsic semiconductor. Okay, so like suppose I have, this is the valence band and this is the conduction band. Okay, and the energy gap between this is called the forbidden gap. So more energy required, like for the germanium, if I'm talking about the germanium, so for the germanium, this energy gap or forbidden gap is a 0.7 electron volt, and for silicon it will be 1.1 electron volt. Okay, so germanium valence band to conduction band, if you want to conduct the electron, it required 0.7 electron volt energy, and for the silicon it required 1.1 electron volt energy. Okay, but when we are adding the trivalent or pentavalent impurity, okay, so pentavalent impurity when we are adding, so pentavalent means, suppose I am taking the example of silicon. So silicon will make the covalent bond with the nearby 4 silicon. Okay, now when we put the pentavalent impurity, so that impurity will replace the silicon atom, and it will take the some places, it will occupy the space and it will make the covalent bond with the nearby. When I am adding the pentavalent impurity, so pentavalent means its outer shell 5 electrons are there, 4 electron make the covalent bond with the nearby 4, but 1 electron will not involve in the bonding. Suppose phosphorus I added, so 1 electron will not bonded or will not make the covalent bond, so it is not completely free. It is still bounded with one more thing that you have to remember, means fifth electron of the phosphorus. It is not the free electron. It is still bounded with phosphorus, but it is not making the covalent bond. That's why its energy will be easily you can remove it because it has not involved in the bonding. But it is a not free electron, so that's why directly we cannot take in the conduction band because it is still bounded with phosphorus. But by a small amount of energy, it can come out, it can be the free. So that's why its energy will not lie in a conduction band. Its energy will not lie in a conduction band and not lie in a valence band. Why? It is not involved in the bonding. So N-type, this when we are adding the pentavalent impurity, it makes the N-type semiconductor. Why N-type? N-type means what? When here majority means majority is what? Electron. Majority is what? Electron. So here we call it, when we are adding the pentavalent impurity, for silicon 0.7 and for 0.3. This is the barrier potentials. Shyam, what you are saying, 0.7 for the silicon and 0.3 for the germanium, that is the barrier potential. Okay, I am talking about the forbidden gap. Understood or not? 0.7 and 0.3 or 0.2 basically in the NCERT they have written for 0.2. That is the barrier potential. I am talking about the forbidden gap. Okay, so N-type semiconductor means majority is the electron. Okay, but this electron is not completely free. That's why it will not lie in a valence band. But it is not making the bond, so it will not be in the valence band. Lie in the valence band, not the conduction, not the valence. So they will take the small energy and they will become free and they will jump to the conduction band. So N-type semiconductor make the donor level. N-type semiconductor make the donor level. Donor level means what? If you give a small amount of energy to the N-type semiconductor, this electron will jump and it will become free. So it will go to the conduction band. Earlier we required more energy, like for silicon I required 1.1 electron volt, and for germanium I required 0.7 electron volt. But when I add the pentavalent impurity, fifth electron is require almost nearly 0.01 electron volt to the 0.05 electron volt. So when you give this much of energy, so what will happen? This electron will become free and then it will jump to the conduction band. So that's why conductivity increases. Earlier it required more energy, 0.7 or to the 1.1. But now here 0.01 electron volt to the 0.05 electron volt energy when you will give. So electron will jump from the donor level to the conduction band. So electron moves, it means current flows. Okay. So N-type semiconductor make the donor level. That donor level will be close to the conduction band. Everybody got? And here donor level, one more basically energy level created between the valence and conduction band, and that requires a lesser amount of energy. That's why conductivity increase. In N-type semiconductor, majority charge carrier will be the electron. That's why we gave the name N-type. Negative is the majority. It is not the negatively charged. The majority is what here? Electron. Majority carrier is the electron. Here mainly current conduct due to the electron motion. That's why, or we are calling it the N-type semiconductor. So N-type semiconductor charge, majority charge carrier is what? Electron. And they created the donor level near to the conduction band. They created donor level near to the conduction band. So fifth electron energy is not the equal to the free electron energy, but when we give the small amount of energy, they will become free and so they will go to the conduction band. Okay. In P-type semiconductor, P-type semiconductor means now you are adding the trivalent impurity. So again, suppose I am adding the trivalent means aluminium. Suppose aluminium outer shell is 3 electrons. So suppose it took the place of silicon. So it take the place of silicon. So nearby 4 silicon atom are there. But it has the only 3 electrons. So one covalent bond will have the deficiency of electron. One covalent bond will have the deficiency of electron. Why? It has only 3 electrons. So this deficiency means electron lesser, means electron density is lesser. That's why we take as a positive charge. So this is called the hole. So when we are adding the trivalent impurity, then it created the what? Deficiency of electron. That deficiency of electron we call it hole. Hole we consider as a positive charge because it is the deficiency of the electron. Okay. So in the P-type semiconductor, so that's why here we say it is a P-type. P-type means what? Here majority is what? Holes. Holes we are considering the deficiency of the electron. That's why hole we consider as a positive charge. So positive charge, that's why we gave the name is the P-type. So in the P-type semiconductor, what is the majority carrier? Majority is the hole. Hole means it is a positive. So that's why we take the P-type. Now here what is happening in the P-type semiconductor, they can take the electron because they have the deficiency of the electron. So they can take the electron from the nearby atom. Suppose some electron is going, it can fill this vacancy. Okay. So they are the acceptor. They can accept the electron from the other covalent bond. They can accept the electron. So P-type semiconductor develop the acceptor level. It develops the acceptor level that will be closer to the valence band. That will be closer to the valence band, and here also energy gap will be between 0.01 electron volt to the 0.05 electron volt. So P-type semiconductor develop that acceptor level because they can receive the electron from the valence band, and N-type semiconductor develop the donor level. It will be closer to conduction band, and acceptor level will be closer to the valence band. That is the N-type and P-type semiconductor. For any semiconductor, this relation we have to remember: number of electron into number density of the hole in extrinsic semiconductor is equal to Ne square or NH square in intrinsic semiconductor, we can say. In the intrinsic semiconductor, number of electron and number of hole will be equal. In intrinsic semiconductor, number density of the electron and number density of the hole will be equal. Okay. So for any semiconductor, product of the number of electron density and the hole density product will be what? Constant. So it will be constant, so it will be equal for the intrinsic also at a given temperature, we can say, at given temperature. Okay, so suppose they have given any intrinsic semiconductor and they are asking, we are doping the trivalent or pentavalent impurity, what is the electron density, what is the hole density they are asking. So we can use this relation, electron density into hole density in the extrinsic semiconductor will be equal to the electron density and hole into hole density in the intrinsic. In the intrinsic both are equal, so directly we can say either the electron density is square or hole density is square. Okay, so one small question in this, if silicon atom density per meter cube and 1 phosphorus atom added per million, they will say ppm. Ppm means parts per billion. 1 phosphorus atom added per million. Then find electron and hole density in extrinsic semiconductor if at that temperature electron density in pure silicon is equal to 10 to the power 20 per meter cube. Okay, taking 10 to the power 15. So here what I'm saying, if silicon atom density is the 5 into 10 to the power 28 per meter cube and we are adding the 1 phosphorus atom per million, okay, then I'm asking what, find the electron and hole density in the extrinsic semiconductor. So when we are adding the phosphorus pentavalent atom, it means it will create the n-type semiconductor. So in this cases what we will take, after adding it become the extrinsic. So we know that at a given temperature product of the electron density and hole density will be equal to the Ne square or NH square. Okay, what is the number of the electron or hole density we will take in extrinsic? So directly how much atom you have added, trivalent or pentavalent. Like suppose you have added the trivalent, so hole density you will take number of trivalent atom added. I repeat again, suppose you are adding the trivalent atom, so trivalent atom when you are adding, so it will create the p-type semiconductor. So in that case, hole density what you will take, you will take number of the trivalent atom added, number density of the trivalent atom added. If you are adding the pentavalent impurity, so what is the Ne you will take in that pentavalent impurity, so it will create the what, n-type semiconductor. So how many, what is the electron density you will take? The number of the pentavalent atom added. So directly number density of hole or number density of electron, we will take directly number of the trivalent or pentavalent atom added. After that we will use the relation Ne into NH for extrinsic is equal to Ne square or NH square, okay, for intrinsic. So here how many atom we have added? One more thing, just a minute. Here I have given 28. So here 15, 30. No problem. Okay. So now silicon atom, total silicon, how many per meter cube we have? 5 into 10 to the power 28. And per million we are adding what? One phosphorus atom. So per meter cube, how many phosphorus atom you have added? So per million phosphorus atom added, we can say what? 5 into 10 to the power 28 upon 10 to the power 6. Why? In 1 million we are adding 1. In 1 million we are adding 1. So in 1, how much you will add? 1 upon 10 to the power 6. So in 5 into 10 to the power 28, how much you will add? 5 into 10 to the power 28 upon 10 to the power 6. So that you got 5 into 10 to the power 22. So how many phosphorus atom you have added? You have added the 5 into 10 to the power 22 phosphorus atom per meter cube. Number of phosphorus atom per meter cube you got 5 into 10 to the power 22 per meter cube. Okay. Now I'm asking the hole density and electron density. Hole density and electron density. So number of phosphorus atom added, that will be directly the electron density we can take. So any in the extrinsic semiconductor, what you will take? 5 into 10 to the power 22. Why? Because how many number of atom you have added? What is the number density you have added? If you have added trivalent, so directly you will take the hole density is equal to that. If you have added the pentavalent, directly you will take the number pentavalent, then electron density will take directly equal to that. So number density for electron in that extrinsic semiconductor, we got the number of pentavalent atom added, that is a 5 into 10 to the power 22 per meter cube. Okay, and they are asking the hole density now, that we don't know. Okay, in the intrinsic they have given the number of electron density is the 10 to the power 15 meter cube. In intrinsic semiconductor both will be equal, so I can say what? Ne into NH. For extrinsic, that we can say what? Ne square or NH square. Okay, Ne in the extrinsic we have 5 into 10 to the power 22. NH I want to find. Ne square is what you will get? 10 to the power 30. Now 10 to the power 30, so then this and this will get cancelled out. You got the 10 to the power 8, and from this we will get the NH is equal to what? NH is equal to 10 into 10 to the power 7 by 5, that is equal to 2 into 10 to the power 7 per meter cube. This is the hole density in that extrinsic semiconductor. Everybody got or not? So they will use they have used the NCERT solid example ppm word. ppm means parts per million, means 1 million we are adding the 1 million per million atom. Per million silicon or germanium, we are adding the 1 atom. According that, we can find the number density of the atom added, pentavalent or trivalent added, and then we will use this relation. Okay. Earlier, we can think like when before adding, we have the hole is what? 10 to the power 15 per meter cube. But after adding, electron is increasing. Okay, electron is increasing. But why the hole has decreased? You can see here. Earlier, before adding, we have the 10 to the power 15 per meter cube number of electron and number of hole. But after adding, electron increase, but hole become what? 2 into 10 to the power 7. Why it is decreasing? Because when you will add more electrons, so they will recombine. They will recombine, so number of the hole or hole density will decrease. That's why what is happening? We are getting the hole density, we are getting lesser than before. Lesser than before adding. Before adding, we have 10 to the power 15. After adding, how much we have? 2 into 10 to the power 7. Why? Some of the electron they will recombine and they will fill the hole. That's why hole density will decrease. Okay. Completed. Now, then we'll come to the diode PN junction first. So what is a PN junction? So P type, N type semiconductor we know. So suppose you have the silicon, pure silicon atom or intrinsic semiconductor. Now you want to make the PN junction, means P and N, P type semiconductor and N type semiconductor you want to combine. For this purpose, we don't take the P and N separately and we put it. We use any adhesive to stick it. We don't do. Why? Because surfaces are rough, so what will happen, the distance between the, when you are putting them, then also distance between, due to the roughness of the surface, the distance will be more than the atomic distance, so that's why it will not work. So if we want to make the PN junction, we want to combine, make one side P, one side N, we want to develop, what we do, like suppose I want to, in silicon atom, intrinsic silicon atom I have, from one side I will diffuse trivalent atom, and from other side I will diffuse pentavalent atom. Okay, one side diffuse trivalent atom, one side we will diffuse the pentavalent atom. So what will happen, where I am diffusing the pentavalent atom, that side it will make the N type, where I am diffusing the trivalent atom, it will make the P type. Now due to the diffusion, one side, like majority here will be what, this will make the N type semiconductor and it will make the P type semiconductor, and it will develop the PN junction. Okay, so in that case, what will happen, when we are diffusing the pentavalent and trivalent atom from the different side, so due to the difference in concentration, because when we are putting the pentavalent, it will create the majority is the electron, from where we are putting the trivalent, it will, the majority will be the hole. So what will happen, here electron density more, here hole density more, so due to the concentration difference, they will go in this side, they will move in the opposite direction, like electrons will go this side and holes will move, we can say, this side. So electron, when they are going to the hole, so they will fill the hole. When they will fill the hole, what will happen, before that P type, N type was the neutral, their majority was the, here majority was the electron, here majority was the hole, but they do not have the charge. Why? Like silicon and aluminum, when we are adding or when we are mixing, making the extrinsic semiconductor, so silicon does not have charge, aluminum does not have charge. So after making the N type or P type semiconductor, it does not develop any charge. Net charge will be number of proton and number of electron will be same. So intrinsic semiconductor, like either it is a trivalent or pentavalent, they are the neutral. So this P type is the neutral, this N type is the neutral. But when the electron is going this side, so that electron is filling the hole. That electron is filling the hole. So now earlier they were neutral, now they receive the electron, so they become negative charge. And which atom, that pentavalent, which atom release the electron, it becomes the positive charge. So what will happen, from the N side, pentavalent atom is releasing the electron and trivalent atom is receiving the electron. So that's why from the, in the P side, negative will be developed and this side positive will be developed. What are these positive and negative charges? These positive and negative is not the electron and hole. This positive and negative charge is the immobile ion. This positive means what? The atom who has given the electron. These are the atom who has given the electron. And what is this negative charge? These are the atom which has received the electron, So what they make the PN junction on the P side positive, on the N side we have the positive charge develop, and the P side negative charge develop. I'm not saying the majority charge developed due to what? Electron, N type, that semiconductor, they given the electron to the hole, so hole receive the electron, it become negative charge, so that is a negative atom. And which atom has given the electron, that become the positive charge. So now positive develop in the N side and negative develop in the P side. So this is called the depletion layer. So depletion layer is what? Depletion layer means when it formed due to the immobile ion. So these positive and negatives are the immobile ions. Okay, and when they are developing like this, so you can see N side positive, P side negative. So it will develop the electric field, and that electric field direction, we know that it is always directed from the positive terminal to the negative terminal. So electric field will directed from N side to the P side or positive to the negative. Okay, so here I have not put any battery or anything. I directly just diffuse the trivalent and pentavalent atom. So if I am saying without any potential external potential difference, what is the which will be at higher potential, N or P? So we can say N will be at the higher potential because N side we are getting the positive and P side we are getting the negative. Okay, What is the direction of the electric field? Direction of the electric field is from the N side to the P side. Everybody got or not? So this immobile ion means what? They make the depletion layer. So depletion layer formed due to the immobile ions. Okay. So what will happen now? Due to the concentration difference, electron was going from N side to the P side, and holes was going from the P side to the N side. This process is called the diffusion. This process is called the diffusion because they are crossing, the electrons are crossing to the N to P, they are going, and holes are going from P to N. So holes means positive charge. Positive charge is going from P to N, means positive charge current, we can say, in this direction, because holes are going from P side to the N side. Electrons are going from the N side to the P side. Electrons are going from N side to the P side. Current we take always opposite to the direction of the motion of negative charge. Current direction we take the opposite to the negative charge motion. Negative charge electron is going to the left, so due to the electron, where the current will go, we will take it towards right. So due to the electron also, we will get the current to the right, and due to the hole is the positive charge, so direction of the current is in the direction of the hole. So you can see the current is flowing from P to N, and that current is due to the diffusion. So that current is called the diffusion current. So what is the direction of flow of the diffusion current? Diffusion current flows from the P side to the N side. Diffusion current flow from the P side to the N side. Okay. So diffusion current P side to the N side. Okay. Everybody got this or not? Now, when this electric field develop, you can see this electric field develop here. Okay. Now in the P side, some P side majority is the what? Majority is the hole. N side majority is the electron. But P side holes are the majority, but some electrons will be there. That is called the minority charge carrier. So in the P side, majority is the hole, minority is the electron. In the N side, majority is the electron, so minority will be hole. Okay. So in N side, some holes are there, we can say, some positive charges are there, and more negative charges. And P side, more positive charge, more holes are there, but some negative charge are also there. Okay. So when electric field is developing, so what will happen? What is the direction of electric field? That is from the N to the P. So electric field will apply the force. If you see the majority hole, they will experience the force in the direction of the electric field. So now hole cannot go cross to the depletion layer. One more thing, electron will experience the force in the opposite direction of electric field. So electron will experience the force in the opposite direction of the electric field. So electron will experience the force to the right. So now electron cannot go to the P type and hole cannot go to the N type. Okay. So it means this electric field will decrease the diffusion current, we can say. This electric field will decrease the diffusion current. And one more thing will happen. This electric field is directed here. So minority carrier in the P side is what? P type, minority is the negative. So they will experience the force opposite to the electric field. So this negative will go to the N side. And N type, what is the minority? Minority is the positive. This positive charge will experience the force to the left. So in the case, due to the development of this depletion layer field, it will stop the diffusion. It will decrease the diffusion. Why? Majority hole, they will experience the force to the left, and majority electron, they will experience the force towards the right. So they cannot cross the depletion layer now. But minority carrier, they will experience the force, like if the electric field is directed here, so this electron will experience the force towards N type, and this hole will experience the force towards the P type. So minority charge carrier will start moving from, like hole will from N to the P and electron from P to the N. So here this current, the current due to the electric field, the flowing due to the minority carriers due to the electric field, that current is called the drift current. I repeat again, due to the concentration difference, current is flowing from the P side to the N type. From P type to the N type, current is flowing. That is called the diffusion current. Diffusion current is coming due to the concentration difference. But here, due to the electric field, current is flowing. Electric field current is flowing, but it is in the opposite direction. It is flowing from N to P. It is flowing from N to P. Why? Positive hole are going to the left, electron is going to the right. So electron motion opposite to the current will be there. So means current you will get from N side to the P side. This current is coming due to the electric field. This current is called the drift current. So drift current flows from N to the P. Diffusion current flows from P to the N. Everybody got or not? So drift current, diffusion current is from P to N, and drift current will be from N to P. This is due to barrier electric field, due to the electric field in depletion layer. Okay. So drift current, diffusion current, that everybody got. So this already asked earlier also. What is the direction of the diffusion current and drift current? So diffusion current is from P to N. Drift current is from N to P. Diffusion current is due to the concentration difference, and drift current is due to the barrier electric field or electric field developed in the depletion region. Okay. And in the when we are not putting any external voltage, so drift current and diffusion current will become, after like some time, it will become equal. So diffusion is going from P to N, drift is going from N to P, so net current you will get 0. So when we have not put any battery, any connection is no, we have not applied any potential difference, then net current will be 0. So that is called the unbiased condition. Unbiased condition means we have not applied any potential difference. Then in that case, drift current and diffusion current will be equal, and they will be in the opposite direction. So net current will be 0. Okay. So then we can say in unbiased condition, diffusion current is equal to drift current. So I net will be equal to what? 0. So no current will flow in the case of in unbiased condition. No current will be there in the diode. Okay. Now then, biasing of the diode. There are the two types of biasing. Biasing means when we are connecting the diode with the external source. So that is one is the forward biasing. Forward biasing is what? When P side is relatively at higher potential than N side, then it is forward biasing. Okay. And when P is at lower, then it is called the reverse biasing. Reverse biasing is what? When N side is relatively higher potential than P side, then it is called the reverse bias. Okay, forward bias when P is at the higher potential. Higher means I'm not saying the positive, means it should be the higher potential with respect to the N side. Then it is called the forward biasing, and if the N side is the relatively higher potential than the P side, it is called the reverse biasing. Okay, so already this that type of question asked. Suppose I am saying Which is the forward biasing, which is the reverse biasing? So this is the, like, this we write as, they take as a P, this we take as a N. So first one, P is at 0, N is at -2. So P is at the higher potential in comparison to the 1. So first one is the forward. Okay. Second one, it is the grounded, means 0 potential. P is at 0 potential and N is at 2 volt. So N is at the higher potential than the P side. So it is the reverse biasing. Okay. And here P is at -2 and N is at -3. Okay. So P potential is more than the and why N is -3? -3 is the lesser than -2. That's why here also it is a forward biasing. Okay. FB, FB, RB. 1 and 3 is the FB and second one is the RB, reverse bias. Okay. Next, something you have to remember in forward biasing, thickness of depletion layer decreases. Okay. And in reverse biasing, thickness of depletion layer increases. Okay. In forward biasing, like suppose now forward biasing, reverse biasing, how will represent? Suppose this is the PN junction. When P is at higher, N is at lower, then it is called the forward biasing. So this is the forward biasing. In the forward biasing, depletion layer thickness decreases. Suppose depletion field here is a V0 and you are applying the V. So what is the net potential here? V you are applying forward and V0 is the reverse. So net potential here you will get V minus V0. So in the forward biasing, suppose you have connected the 2-3 diode, all are the identical, and you put all in the forward. So in the forward biasing, all will have the same potential. All will have the same potential because in the forward biasing, all will behave like a equivalent. Why? Because reverse potential is a V0, applied potential is suppose V1, so V1 minus V0. Another is also identical, so same potential drop. Another also identical, same. So in the forward biasing, all diode will behave identical. If all the diode have they are made of silicon, they are the germanium, they are identical. So potential drop across the all diode will be same in the forward biasing. Potential drop across all the diode will be same in the forward biasing. Okay. In reverse biasing, what will happen? Now suppose depletion field is the V0 and now you applied the V. So what is the net potential? Here you will get V plus V0 because reverse potential will increase. So in that case, depletion layer will be more thick. One thing. Second thing, reverse biasing. Suppose you have connected the 2 diode in the reverse biasing. 2 diode in the reverse biasing, both diodes are identical. Then potential drop across both diode will be same. In reverse biasing, potential, like both are in the reverse, so potential drop across the both diode will be same. If both are in the forward biasing, then potential drop across them will be same. But suppose one is the forward biasing, one is the reverse biasing, then potential drop will be different. Like suppose I am saying this. So if I'm asking what is the potential drop, V1 and V2 are here, what is the relation between V1 and V2? So if you see this, so suppose here potential drop total I'm taking V1, here I'm taking V2. So first diode is in the forward bias, this is in the forward bias, and you can see this is in the P side as negative, P is at the lower potential, so this is the reverse bias. So one is the forward bias, one is the reverse bias. So in this case, potential drop across both will be different. So V1 is not equal to V2. V1 is not equal to V2. Why? Because both are in, one is in the forward bias, one is in the reverse bias. If suppose I have given both in the forward bias, then V1 is equal to V2. If I have given both in the reverse bias, then V1 will be equal to V2. But one is the forward bias, one is the reverse bias, then potential drop will be different. Understood? So this is the barrier potential from P side to the N side that figure has given. So this is the barrier potential. This is the V. V is the barrier potential. So 2-minute break. This is the this one. Suppose I am saying 1, 2, and 3. 2 I have set the unbiased. 2 I set the unbiased. Then who will say what is the 1 and what is the 3? What is the 1 and what is the 3? In forward biasing, barrier potential decreases. In forward biasing, barrier potential decreases. In reverse biasing, barrier potential increases. So second I have shown the unbiased. Second is the unbiased. So one barrier potential decrease with respect to unbiased. If you see one barrier potential decrease with respect to unbiased. So one is what? Forward or reverse? One is what? Forward or reverse? One is the forward biasing. Why? Because here barrier potential is the lesser than the unbiased. So this will be the forward biasing and this will be the reverse. Why? Barrier potential is more than the unbiased. So first one will be the forward, third one will be the reverse, second one is the unbiased. If I have given the second one is the unbiased, then 1 will be the forward, 2, 3 will be the reverse. Okay. Okay, take the 2-minute break. Okay. Now diode as a rectifier. So diode as a rectifier we use as a half wave rectifier and the full wave rectifier. Rectifier means what? Suppose we are applying the alternating current, but through the load current is flowing in the same direction. Then we can say the current get rectified. So half wave rectification means only one cycle. Like one cycle is the positive in the case of alternating voltage, and half cycle positive, half cycle negative. So if only half cycle get rectified, means current is flowing through the load only for the half cycle, and next cycle current is not flowing, so it is called the half wave rectification. If current is flowing in the same direction for both positive and negative cycles, so it is called the full wave rectification. Okay, so half wave rectification, this is a suppose circuit diagram. So in this case, what will happen when you are applying the alternating voltage? Okay, sinusoidal, suppose you are applying. So for the positive cycle, this will be positive and this will be the negative. For positive cycle, this diode will be in the forward bias, so it will conduct the current through the load. So positive cycle we will get through the load. For negative cycle, what will happen? This will be the negative, this will be the positive. Then it will be in the reverse bias. It will be in the reverse bias. It will not conduct the current. And one more thing that you have to remember, forward bias, if they have not mentioned, forward ideal diode forward bias offers the zero resistance, and reverse bias it offers the infinite resistance. Ideal diode in forward bias offer the zero resistance, and reverse bias it offers the infinite resistance. If they have mentioned in the problem like the diode offer this resistance in the forward bias, that we have to take. If they have not mentioned, so we have to take the diode as a ideal. Ideal diode forward bias zero resistance, reverse bias infinite resistance. Okay, so this is the half wave rectification circuit. Why? Because the current through the load will go for only half cycle. Okay, so this is the half wave rectification. Full wave rectifier, what will be the circuit? Suppose we are applying the alternating voltage. This is the load resistance, and here we have added the two diode D1 and D2. Okay, here we are applying the alternating source. Then in that case, what will happen? So D1, suppose you are applying the sinusoidal voltage. So first, for the D1 at t is equal to 0, you will get positive, negative like this. T, this is the voltage. At t is equal to 0, here I have mentioned, this is the sinusoidal. So in a D1, what will happen? At t is equal to 0, positive cycle incident, then next negative cycle, then positive cycle, then negative cycle. So for the D1, I have made what is the incident waveform? First positive, then negative, then positive, then negative. In D2, what will happen? If the D1 positive, then D2 will receive first negative. So for the D2, what is the waveform it will receive? D2 will receive first negative, then positive, then negative, then positive, like that way. I repeat again, suppose we are applying the sinusoidal waveform. So D1 at t is equal to 0, D1 is receiving the positive cycle, positive half cycle. So D2 will receive negative. Okay. Then second half cycle, D1 will be negative, then D2 will be positive. Next half cycle, D1 will be positive, D2 will be negative. Like that way, it will incident. Okay. Now, when D1 is receiving positive cycle, means this is the positive, this is the negative. Means D1 will be in the forward bias, D2 will be in the reverse bias. Now, what will happen? Current will conduct through the D1, not from the D2. So, current will go through the load in this direction. So, positive half cycle, current flown due to the current flowed through the due to the D1. Why? D1 conduct the first cycle. So now I am making the after rectification. After rectification, what will happen? First, you got the cycle. This cycle you got due to the D1, because D1 has conduct the current through the load. So this first half cycle you got due to the D1. Next, what will happen? D1 negative cycle will incident and D2 positive cycle. So D2 positive cycle means this will be the positive, this will be the negative. Now what will happen? This is positive, so D2 will be in the forward bias, D1 will be the reverse bias. So D2 will conduct the current and then current will go through the load due to the D2. In the same direction it will go, this direction. Getting or not? So second negative cycle, current conducted through the load in the same direction but due to the D2. So next cycle you will get the same direction current but that you will get to the D2. Then again next cycle, next half cycle positive on the D1, negative on the D2. So this will be again positive, this will be negative, so current conduct due to the D1, then you will get again due to the D1. Like that way alternate cycle you will get due to the D1 and D2. Understood or not? So this is the waveform of the incident voltage on the D1. This is the waveform for the incident on the D2. Okay, and this is the after rectification through the load we are getting this D1, D2 we are getting according to that. Why? First current is conducted due to the D1, then next half cycle current conducted due to the D2, and like that way it will go alternately. Okay. In the place of this, suppose they have given the any other, not sinusoidal, they have given the constant voltage like this type of, already in the NEET they ask, like this type of waveform they are saying. So this is also the alternating, because but here it is not the sinusoidal, it is a constant. For positive cycle, like they have given 5 volt, and for negative they have given -5 volt. So if it is a full wave rectification, so directly you will get the 5 volt constant. If it is a half wave rectification, so output only what you will get 5, negative get cut, then 5, then negative get cut. So half wave rectification, then what you will get? Then after half wave rectification, only positive cycles we will get, negative cycle will get cut like this. Okay, if it is a full wave rectification, we will get the constant. Okay. Completed. And if you want the, up to this, okay. Now that is a half wave and full wave rectification. Now first I am coming to the photodiode. Photodiode is what? Photodiode, it works in the reverse bias. Why it works? What is the use of the photodiode? Photodiode we use to detect the optical signal. Okay, so which signal photon energy or which light photon energy is the more than the energy gap, so they will absorb the photon and the current will flow. Okay, photodiode is used to detect the optical signal and it works in the reverse bias. It works in the reverse bias, that you have to remember. Solar cell and the light emitting diode. Light emitting diode, it convert the light energy into the electrical energy. It convert the light energy into the light is falling on that, electrical energy it convert into the light energy. LED convert electrical energy into light energy. LED convert electrical energy into the light energy. Photodiode, it is used to detect the optical signal. Okay, solar cell is used to develop the potential difference. Okay, these three characteristic curve you have to know. Now directly I am coming what? Transistor. If I'll enter, it will take time. First I am completing the gate 1 or 2 question I will discuss. Okay, so logic gate, we know that mainly OR gate and AND gate and NOT gate. Okay, and NAND gate and NOR gate, they are called the NAND gate, and NOR is called the universal gate. Okay, AND gate symbol everybody know, like this is the symbol for the AND gate. When A and B, then output what you will get A dot B. OR gate, A plus B, when the input is the A and B. NOT gate, when A is the input, A bar will be the output. Okay. In the problem of the gate, so like combination of the gate, they are saying on how to convert the NOR gate into the AND gate, like that way number of gates they are asking. So if suppose I have given this circuit, what is the output of this gate? What is the output of this gate? So here I am using the 3 NOR gate. I am asking what is the output of this gate. It will behave like a OR gate, it will behave like a AND gate, it will behave like a NAND gate. Okay, so here it is a combination of the 3 NOR gate. 3 NOR gate output I am asking. So one thing you have to directly remember, what is the output? It will behave like a AND gate. Okay, so here A and A, both signal we are putting, then here we will get what? A plus A bar. A plus A is equal to what? A, and then here the output what you will get? A bar. Here output what you will get? B bar. Now A bar and B bar is the input of this gate. So here what you will get? A bar plus B bar. This is the first OR, and then after that you have to apply NOR. So this is the what? A bar plus B bar whole bar. Now A bar plus B bar, what I can say? A dot B whole bar, and already one bar is there. Now bar and bar, even times of bar will get cancel out. So what you got here now? A dot B. Now A, B, I have taken input and I am getting what? A dot B. It means this whole combination behave like a AND gate. So we have to remember what? Now same case, if suppose you want to make the OR gate by using NAND. So all these gate you will replace by NAND gate. All these gate you will replace by NAND gate, and A and B you will take. So here you will get what? A plus B. So NAND will get converted into the OR. So if you want to convert NOR gate to the OR gate, so number of gate required is equal to 2. Then NOR gate to the AND gate, number of gate required is equal to 3. Like you can see here, NOR gate to the AND, how many gate I have taken? 3 gate. Okay. Similarly here, NAND to the AND gate, number of gate required is equal to 2. Okay. And NAND to the OR gate, then number of gate required is the 3. Then NOR gate to the NAND gate, then up to the end you require the 3. NAND gate we require the number of gate, for this we require the 4. Okay, and NAND to the NOR we require number of gate is equal to 4. Okay, these directly you have to remember. NOR to OR, NOR to OR 2, NAND to AND, NAND to AND, that I have written 2, NAND to AND 2. Okay, NAND to AND 2, NOR to OR 2, NOR to AND 3, NAND to OR 3. Okay, NOR to NAND, up to the end we are requiring 3, but we required NAND, so that extra 1 gate will require 4. Okay, these directly you have to remember. Okay, now you will say this gate will behave like what? Suppose now suppose I am saying it will be the equivalent to the OR gate, NAND gate, AND gate, NOR gate. So you have to find the output. Input we have is taken the A and B. According to the output, we can decide it will behave like a AND gate, NOT gate, OR gate, what? Okay. So here, De Morgan's law we have to remember. De Morgan law is what? For the summation, for the product. So for the summation, like A plus A, that is equal to A. Second, A plus 0 is equal to what? A. Third, A plus 1. If anything you are adding in 1, always you will get what? 1. Okay, this is for the addition. Now next, for multiplication, A dot A is equal to A. Then A dot 1, that is equal to A. And next, A dot 0, that is equal to 0. Okay, these are the for product. Next, for the bar, A plus A bar that is equal to 0. Sorry, A plus A bar that is equal to 1. Okay, because suppose A is the 1, A bar will be 0. 1 plus 0 is equal to 1. Suppose A is the 0, then A bar will be 1. 0 plus 1 is equal to 1. So A plus A bar is equal to 1. And A dot A bar is equal to 0. Because their product A is 1, A bar will be 0. So 1 into 0, 0. If A is 0, then 0 into 1 will be equal to 0. Okay. Next, two more. That is a plus B whole bar. A plus B whole bar, what we will say? We have to change the what? Sign means A dot B, and we have to apply the bar separately. A bar dot B bar. Next is the A dot B whole bar. Then again we have to change the sign and apply the separately. So what you will get? A bar plus B bar. Okay, this law we have to remember. A plus B whole bar is the A bar dot B bar. A dot B whole bar is the A bar plus B bar. Okay. Now here, who will say what is this gate? So in this problem, what we'll take now? What is the input of the first? Suppose I mark this is the first gate, this is the second, this is the third. Okay. So first gate, what is the input? A, and what is the input from here? This is a B, not the B bar. Here input is a what? B. So here output what we got? A dot B whole bar. Okay. Here what is the output? A is coming from here, B bar is coming from here. So A dot B bar. This is the output here. Okay. Suppose this I am taking the X, this I am taking the Y. Now what is the input of the third gate? Third gate input is the X and Y. When larger input is there, we have to assume like X and Y. Okay. So input of the gate third is the X and Y. It is a NOR gate. So what it will give? X plus Y whole bar. Okay, X plus Y whole bar, because it is a NOR gate. X plus Y whole bar. Now I can use the De Morgan's law. Now output, suppose I am writing X plus Y whole bar, that I can write what? X bar dot Y bar. Okay, X plus Y whole bar is the X bar dot Y bar. What is the X now? X we have taken what? X we have taken A dot B whole bar. A dot B whole bar, and again you have to take the bar. So if I put the value of X now, so A dot B bar, this is the X and whole bar. Dot, what is the Y? Y is the A dot B bar and its whole bar. Okay. Now bar and bar, even times of bar, it get cancelled out. So what we got? A dot B. Okay. And here what we got? A dot B bar whole bar. A dot B bar is equal to what? A dot B bar is equal to what? A bar plus B bar. So then you will write here A bar plus B bar. Already B in the place of B, we have the B bar. When we put the B bar, so B bar cancel out, we got the B. Again I am repeating A dot B bar. If it is a dot B whole bar, you will write as the A bar plus B bar. But in the place of B, we have B bar. So bar and bar will get cancel out. Now this when you multiply, so what you will get here? A dot B dot A bar plus A dot B dot B. When you separate it, you got this. A dot A bar. A dot A bar, what you will get? 0. A dot, whatever the value of B doesn't matter. A dot A bar, what you will get? 0. B dot B. B dot B. A dot A, what you will get? A. Similarly, B dot B, what you will get? B. So then what you got? A dot B. A dot B, it means it is a what? Output is the AND gate. You have started with AB input, but what is the output you are getting? A dot B. So this circuit is equivalent to the AND gate. Everybody got or not? Completed? Now NEET 2019 question, that was the circuit diagram. So suppose it is a 5 volt they gave, and here they given the bulb. What was the thing? So they ask this circuit is equivalent to what? Okay, so one input they are taking here, that the switches they are taking, the input is the A and B. This is the A, this is the B. Okay, now here they are applying the 5 volt. 5 volt when you apply, so A and B two input, and here output we are taking across the bulb. Okay, bulb is glowing, so output is 1. Bulb is not glowing, so output is a 0. Switch is closed, so 1. Switch is open, then 0. Okay, so here input is what? A and B, and output is what? Y. Okay, now 5 volt here, 0 volt here, so potential difference here 5, here grounded means 0. Now if I close the switch, if I close the switch A, if I close the switch A means A I am taking 1, and I open the switch means B is equal to 0. B is equal to 0. Then what will happen? Current will go from here, but this path is not closed. This path is not closed. Then what will happen? Current will go through the bulb directly. So bulb will glow. So bulb will glow when any of the switch is open. Suppose I close the one, but B is open. B0 means B is open. So this path is open path. Open path, current will not go. So current will directly go through the bulb. Bulb will glow. So that's why output we are getting 1. Now suppose I open the A, close the B. Now I open the A, so then it is still the open path. Current will not go from here, so current will pass through the bulb. So then bulb will glow. Okay. Now I open the both. When I open the both are 0, 0. When both are open, then still this path is the open path, so current will directly go from the bulb. Bulb will glow. So this is 1. Now I close the both switches. When I close the both switches, A and B both are closed. So we will get the one closed path here. When closed path here, so current always flow through the minimum resistance path. So this bulb will get shorted. Why? It is connected with the closed conducting path. So when the current will go from here, it will not go through the bulb. It will go from here to here. It will go from here to here. So what will happen? Current will not pass through the bulb. So when both are closed, so current will get one closed conducting path. So it will not pass through the bulb. Then bulb will not glow. When both switches close, then bulb will not glow. So we know that in the case of AND gate, when any input is 0, so in the case of AND gate, we will always get 0. But here what is happening? If any input is 0, then we are getting 1, and both input is 1, then we are getting the 0. It means it is what? NAND gate. So this circuit will be equivalent to the NAND gate. Okay, so this is about the gate circuit diagram of the OR gate, NAND gate, you know that. Okay, atom and dual nature, like it is a small topic, most of the things you know. So in that, I think not more required. Mainly I focus on the theory part of the semiconductor. Okay, so atom and nuclei, you can read EM waves, basic DOP and displacement current, that you have to complete. Okay, because now the another class is there. Okay, okay, so if anybody has doubt in the atom, or you can send the WhatsApp. Okay, I will tell the doubt. Okay, then bye bye.